Welcome to Ready to Derive. In this video, we are going to explore the standard form of a linear equation. There are standard forms for quadratics, circles, etc. But we are dealing in this video with lines, equations of lines. So standard form is of the form ax plus by equals c. If that looks familiar to you, no problem, because you're going to learn a lot more about how to use it. And if it's unfamiliar, I'm going to show you what it means and how it arises, in particular, looking at examples of real-world scenarios that lend themselves to standard form. As a prerequisite, you should know that y equals mx plus b, which is slope-intercept form, and point-slope form, because we will refer to these a couple of times. But without further ado, let's get started. So let's begin with a scenario that gives rise naturally to standard form. So here we are. I have $2 of change in my pocket comprised of quarters and dimes. And what are the possible combinations of coins I can have? Well, let's create a table to think about this. We'll put quarters in the left-hand column, dimes in the right-hand column, and go from there. So even though it says I have quarters and dimes, let's just, for the sake of finding kind of the intercepts of this equation, imagine that I had no quarters, actually. If I had no quarters, that means all $2 of that money would have to be dimes, which means I would have 20 dimes. Let's build up from there. Say I had 1 quarter. 1 quarter would be 25 cents, which would leave $1.75 on the dime side. And I cannot have dimes adding up to $1.75, so it seems like I can't have an odd number of quarters. Let's check 2 quarters. That would be 50 cents, leaving $1.50, 15 dimes. 3 quarters, I don't think I can do again because it will leave an odd number for the amount the dimes have to make. So let's go to 4 quarters. 4 quarters would be $1, leaving $1 for dimes, making 10. And similarly 6, where I think we can see the pattern in the table, right? Every time you go up 2 in quarters, naturally, 2 quarters is 50 cents. Naturally you gain, or you lose 5 dimes as a result. So that would be 5. And if I had 8 quarters, that would be $2. I'd have nothing left for dimes. So that table looks about right. So let's think about why this makes sense in terms of why this leads so easily to writing an equation. Because we realize that if we have however many quarters we have, they're going to be worth 25 cents. And however many dimes we have, they're going to be worth 10 cents. And that has to add up to $2. So that's an example of an equation in standard form. Now, it's not quite standard form because there's some stipulations of these numbers that go in front of the variables. They're called coefficients. They actually have to be integers. So we could multiply everything by 100, both sides by 100. We get 25q plus 10d equals 200. And now there's some other stipulations. So that's multiplying by 100. The other one is that they should have no common factor. So we could, in fact, just divide by 5. And we'd get 5q plus 2d equals 40. And that here is an example of an equation in standard form that arose naturally from this scenario. And there's one more thing. If we were to graph the data points in the table, so dimes on the y-axis, for simplicity, quarters on the x-axis. There's our first value there. There's our y-intercept. Let me get something to kind of, so there's our y-intercept, 0, 20. And there are the other points. So let's put them in. Now we can see that we could also have written that, if we just looked at the table, graphed it, we could have written that naturally in slope-intercept form. But that would have taken creating the table at first and then the graph, and but from the problem itself, it was very easy to write in standard form. But let's just say we did write it in slope-intercept form. We see the y-intercept is 20, right? So the y-intercept up there is 20. And then we see that the slope, we see that we seem to go down 5, right? Every time we give up 5 dimes, we gain 2 quarters. Give up 5 dimes, gain 2 quarters. So if we look at that, we see that the slope is -5 halves. So in terms of the context of the problem, you have to realize the thing about standard form is that the 5 and the 2 and the 40 don't really sort of bear much relevance, to the context of the problem. You can see that slope-intercept form, actually the 20 and the -5/2 have a lot of meaning, but nothing beats how simple it is to create an equation in standard form. And so let's dive into that in a little more detail. So the standard form of an equation of a line is, as we saw before, ax plus by equals c. It's sometimes also written like this in some textbooks, where they bring all the terms to the other side and it's set equal to 0. And as we saw in the coin problem, standard form arises naturally from real-world contexts. We'll look into that in a little more detail in a moment. And here's some of the stipulations. So, well, first of all, a and b are called the coefficient. C is the constant term because it's not attached to a variable. So here are some stipulations. A, b, and c have to all be integers, and a has to be greater than 0. So if I gave an example, let's see, if I wrote this, 0.5x plus 1.5y equals 3, that's not yet in standard form. If I multiplied by 10, then I would get negative 5x plus 15y equals 30. So that definitely has taken care of a, b, and c being integers. But a also has to be greater than 0. That's not for any profound reason, but just because it sort of makes it neater to write. So we would have 5x minus 15y equals negative 30. And now another stipulation, it kind of makes sense to simplify it as much as possible, is that a, b, and c should have no common factor. So if we divide through by 5 now, we get x minus 3y equals negative 6, and that would be an example of an equation in standard form. And as sort of finally, as we saw in the problem before, the values of a, b, and c, in this case 1, negative 3, and negative 6, don't really have any connection to the features of the graph. As we saw, slope-intercept form gives us a lot more information about the graph. But as we also saw before, standard form is sometimes the easiest form of equation to write. So we're going to look at a few more scenarios that lend themselves to writing equations in standard form. So here we have tickets to a show, $19 of purchase in advance, and $23 at the door. There's the total sales on the night of the show. So to write an equation, of course, we need two variables. So we'll use x and y. And if x is the number of tickets sold in advance and they each are worth cost $19, then 19x would give the total contributed from those sales. And then 23y would be from the sales at the door, and that must add to 5,350. And this equation is truly in standard form because 19 and 23 have no common factors, so no need to simplify that or anything. Here's another one. 60-point tests consisting of multiple choice and short answer questions. So let x equal the number of multiple choice, and they're worth 2 points each. So 2x would give the total points from the multiple choice section, and 5y from the short answer, and that would have to add up to 60. And this next question is actually a real world one, because I actually did this calculation because I was staying at a vacation rental, kind of remote from the nearest supermarket, and all I had was low-fat milk and cream, and I needed to make whole milk. So I actually created an equation. I know it's kind of nerdy, but in order to solve this. So I said let x is the number of cups of low-fat milk, and if that's the case, then I know that 2% of those x cups will be the amount of fat I get from them. And from the cream, it would be 0.10 y. And now here's the tricky one. Now it's not so obvious at first, but we know that we need 3.5% of something. But you just can't have 0.035. You have to have that of something, and that's why I gave you that extra piece of information that I had I wanted to create 1.5 cups of whole milk. So this equation is not technically in standard form because of all the decimals, etc., but you don't have to worry about that when you're interested in just solving the equations. Well, I say equations because there's one more equation that may not be as obvious, which is that x plus y has to add to 1.5. So this is an example, again, standard form creates a system of equations. We will learn how to solve these in another video algebraically, but later in this video we will also treat an example, then we'll solve them graphically. So let's practice converting between standard form and slope-intercept form. So they each have their purposes depending on whether you're solving systems of equations or you're trying to graph. It varies depending on what you need to do. But one thing about slope-intercept form is it can be very messy with those fractions in it, and that's why sometimes it's nice to work in standard form. So the first thing you want to do when you convert to standard form is kind of wipe out all the fractions. So the 4 and 2, the lowest common denominator would be 4, and that will help to wipe them both out. So if we multiply both sides by 4, let me just get that little mark away. Okay, we would get 4y equals 3x plus, so 2 into 4 is 2 times 5 is 10. And now if we bring the variable terms to one side by subtracting 3x from both sides, we would get negative 3x plus 4y equals 10. And if we stick to the principle of keeping the coefficient of x positive and we multiply by negative 1, we would get 3x minus 4y equals negative 10, and we have thus converted to standard form. Now, let's go, and you can see, again, no fractions in there. It's a very easy form to work with and manipulate. But sometimes you just want to convert to slope-intercept form for easy graphing. That would be one of the purposes. So to do that, we're going to isolate y. So we'll subtract 3x from both sides. Now I write it like that. You can't really subtract 3x from 12, so I'm going to write that as negative 3x plus 12. My apologies, let me make that a little neater. There we go. And then you would have to divide by negative 2 on both sides to get y alone. So y equals 3/2 x. The negatives cancel there, but negative 2 into 12 is minus 6. And now you have it in slope-intercept form. It makes it very easy to do sort of rapid sketching. You got the y-intercept, you got the slope, easy enough to create the graph. So we're going to actually practice graphing equations that are in standard form. And this is the same problem from the previous slide. 3x minus 2y equals 12. And of course, one method, as I mentioned, was just to convert to slope-intercept form. So we've done this already. We see that the y-intercept is negative 6, so we could put a point here at negative 6. And the slope is 3/2, so it means up 3 over 2. And we could connect those points and create the line. So up 3 over 2, etc. Just continue that process. But when equations are in standard form, there's actually a really nice shortcut way to also graph them, and that's by finding the x and y intercepts. And if we think about it, the x-intercept, for example, the x-intercept would be a point along the x-axis where the line intersects it. And we can kind of see it. It looks like it's over there at 4, 0. But what do we know is true along the x-axis? One thing that we know is always true is that y equals 0. So this is the trick. To find the x-intercept, we set y equal to 0 and solve for x in the equation. So we have 3x minus 2 times 0 equals 12. 3x equals 12, which means x equals 4. And that means that the x-intercept is 4, 0. Similarly, the y-intercept, oh right, and there's 4, 0. Sorry, let me just clarify that. We sort of saw that coming. And for the y-intercept, we do the same thing. We set x equal to 0. So now we have 3 times 0 minus 2y equals 12. So negative 2y equals 12. So y equals negative 6, which means the y-intercept is at this point 0, negative 6, which we already saw before. And then we can just connect the x and y intercepts like this. And so both methods work. The x and y-intercept method lends itself to standard form, and it's really easy to solve without having to isolate y and deal with fractions, etc. So in previous examples, we've seen how simple it is to write an equation of a line in standard form given a real-world scenario or a context. But it's not so easy to do so when you're just asked for the equation of a line through 2 points. In this case, you have to resort to either slope-intercept form or point-slope form, and then convert to standard form. So I'm going to use point-slope form since we are not given the y-intercept exactly. So let's call this formula up, and slope m, remember, is change in y over change in x. So x2 minus x1, so that would be 0 minus negative 7 over 3 minus 5, which comes out to be negative 7/2. And then we could choose x1, y1 to be either of the 2 points. It's probably easier if we chose 3, 0, but I'm going to use, because we have 0 involved, which always makes things easier, but I'm going to use those points instead. So we have y minus y1, so y minus negative 7 equals negative 7/2 times x minus 5. And that becomes y plus 7. And now what I'm going to do is this denominator over here, I'm going to multiply up to the other side. So I'll get 2 times y plus 7 equals negative 7x plus 35. So that's 2y plus 14 equals negative 7x plus 35. I'm going to bring the 7x to the left-hand side so that it's positive 7x plus 2y, and I'm going to subtract 14 from both sides to get 21. And then we have the equation of the line in standard form. So we're going to end by solving a system of equations graphically. And I'm going to revisit the scenario from earlier in the video with this 60-point test. I'm going to give you some additional information that there are 18 questions on the test. And we know how easy it is to convert these into standard form equations. So remember, we had, if x is the number of multiple choice questions, 2x plus 5, and let y be the number of short answer, and that has to add to 60. But we have this new piece of information, is that x plus y has to equal 18. And if you have two equations with two variables to solve, that's what's referred to as an example of a system of equations. And right now, we will learn how to do that algebraically in a later video, but we're going to approach this graphically. It kind of reviews everything we've learned so far in this video. So we can first of all graph them easily by finding the x and y intercepts. Now, why I like doing this using x and y intercepts rather than slope-intercept form is they're very easy to find. So the x-intercept, of course, remember, is when y equals 0. So we could, when y equals 0, that term disappears, and you just have to divide 2 into 60. So our x-intercept is 30, 0. And let me erase that. And similarly, to find the y-intercept, we put x equals 0. So 0 and 5 into 60 is 12. And we've easy enough to solve. And in the next one, it's even more straightforward. We just see that the x-intercept is 18, 0, and the y-intercept is 0, 18. So then we could graph these on this handy-dandy graph I created. And first of all, here's the intercepts for 2x plus 5y equals 60, and I'm going to connect those. Now, I realize by connecting them, it would be more realistic to make discrete dots because I can't have fractions or decimals in this problem, but for simplicity, we'll connect them like that. And then I will graph the other intercepts and connect them. And then, so solving it means finding where they intersect. And that's pretty easy to read off here, that it's at 10, 8. And what does that actually mean? So x is 10, y is 8. That means there are 10 multiple choice questions and 8 short answer questions. So that brings us to the end of the video. I hope you enjoyed it. If you would like more of this, please do hit the subscribe button at the bottom right-hand corner of the screen.